So in the last lecture, one of the students asked about how this phase changes in the Chebyshev filter and how this rapid change in the phase happens when we have sharpness in the characteristic of filter. See, when you have a sharpness, means that your poles have high Q. High Q means that their real part is small comparative to the poles who have smaller Q. Therefore, the question was, okay, so how this affects on the rapid phase change? See, simply if you look, if you have what is phase essentially? If you have two poles, and definitely both of them should exist because system is a physical system. Therefore, your phase will be tangent inverse omega 0 upon sigma minus tangent inverse, this is in fact omega, this is pole, therefore your polynomial will be S plus sigma plus j omega 0 into S plus sigma minus j omega 0. And S is equal to j omega. Therefore, theta omega will be tangent inverse omega plus omega 0 upon sigma plus tangent inverse omega minus omega 0 upon sigma. Now, if you have reduced sigma, what happens is, if you are close to omega 0, where you are in fact in the vicinity of pole, because sigma is small, here you won't see a change in the sign, but here you will see a rapid change in the sign. And this rapid change in the signs as 0, it is 0. This is the pi upon 2 minus pi upon 2. So it is 0. So this is now, if sigma is very small, means that you are close to this region, which has the highest slope. So that is the reason we observe a rapid change in the phase when we are close to pole. And when this pole is close to omega axis, therefore real frequency that we deal with, which is j omega, is actually getting close to it. So now we will reach here. Because now, in fact, your pole is this, sigma is going towards 0, therefore j omega, when it is close to omega 0, here this is 0. In the case of omega 0, if you will be having something like this, and this will be omega 0. So that is the reason we observe the rapid change in the phase. Therefore, when Q increases, you will see more phase distortion. And there was a factor of 1 upon 2 pi in the first lecture, one of the students mentioned. So you please correct it in the calculation of noise, because noise power spectral density is a function of f. We multiply it by bandwidth and then we integrate it from some frequency f1 to f2. So this is f. Therefore, in the relation I had written in the first one, I used omega, therefore you add a coefficient of 1 upon 2 pi to the integration. And here you will have the omega. These are just two things I wanted to mention so that it will be clear. And only 2 students till now have reported this high pass filter. Both of them got infinite noise by analytical calculations, but I ask you to simulate it. If you simulate, you will see simulator will show something different. So take care, and then your calculation has something wrong, okay? Again, double check your calculation. There is something specific that you have to be careful about it. Otherwise, this means we are not possible to have any type of high pass filter. But we implement many band pass filters in the form of high pass plus low pass. Therefore, there is how a high pass filter doesn't show a very high noise at the output. You simulate, and then that will help you to understand what is happening and why power spectral density of noise actually is not increasing with frequency. Okay, now I hand over to Kaushik. So then afterwards, I will tell you and I will explain for you how high pass filter will operate. But right now, you just think about it. I want you to start thinking and then see what is happening. If I tell you the answer, then you don't learn how to think about this interesting things which happen, and usually they don't have their what I should call, they don't have the first order assumption which makes them correct. And in fact, by first glance, you feel high pass filter should not be. And then when you use analytical calculations also, you see, yes, it is like that. So you should be curious then what is happening. Okay, so one of these, either simulator is wrong, which is not possible, therefore calculation should be right. Then look what is wrong in your calculation.
All right. So what I wanted to do today and talk about some of the integrated systems in the more than more domain. And I'll explain what I really mean by more than more. And the idea is that we'd like to design very low cost but very energy efficient systems of the future. And so in that case, what it turns out is that I feel that one has to sort of use different kinds of heterogeneous devices. And to that effect, actually, I'll be focusing more on the heterogeneous devices and some of the circuit implications from that angle. So Maryam suggested that this is a mixed signal class, and to talk more about analog. And as I earlier said, that I don't work on analog designs, but this is certainly very, very mixed technologies. And since we're using mixed technologies, this is going to be using mixed signal circuits and topologies too. So going through the silicon scaling issues in CMOS, this is something that we have gone over last lecture too, but I thought for the sake of completeness, it's a good idea to talk about some of the scaling issues again. As device dimensions are being scaled, once you go below, for example, 65 nanometers, there's increased process variation, and we talked about it last time, increased leakage current. Turns out that the power density increases, and if you look at some of the chips of today, you're close to about 100 watts per centimeter squared, and turns out that's not a real limit, but again, with today's technology that is available, without any fancy cooling methodologies, turns out it's certainly very difficult to go above 100 watts per centimeter square. Turns out again, based on all these, power density increased variation, one has to also look at reliability. And there are various types of reliability that one has to look at in scale technologies, and bias temperature instability, some of the hot electron effects, and in fact, time-dependent dielectric breakdown. Those are certainly some of the ones that one has to look at. And again, as I mentioned last time also, that if you look at dyes coming out of different wafer lots, there's a good amount of variation between the transistors that you see from, one wafer lot coming from one particular dye to another dye. And on top of that, turns out there is also variation, which is a random variation, and that could be due to, again, random dopant fluctuations or line edge roughness and so on. So if these variations are really, really large, then of course, in order to have high yield, you need to go to the worst case corners of your design. And if you do a worst case design, the unfortunate thing is that your power consumption is going to go up, right? Because, or either you have to scale up your supply voltage, and that means also power consumption is going to go up. And unfortunately, area is also going to have a severe penalty. So it doesn't probably make sense to do the worst case design. So people have been looking at various ways of doing nominal design, but sort of along with the nominal design, considering different error resilient techniques. And that, by the way, I mean, some of these are going to be very, very important in memories, not so much maybe in logic, but certainly very much in memories where, matching transistors are required. So from a mixable point of view, again, certainly, matching turns out to be important. Earlier days when it comes to, for example, analog design, people were worried about those things, not that they're not, worried about today, but what is really important to notice is the fact that some of the things that analog designers were concerned about, in the earlier days, these days, digital designers have to consider that too. So, taking care of, considering which process corner that you're in, then taking some corrective actions, self-tuning, self-correction, they turn out to be actually important in today's CMOS circuits. And again, this was actually showing the power density and some of the plots showing the reliability issues. So the question, of course, is that, I mean, these are some of the things that are going to be there, and are these going to be the showstoppers for scaling of CMOS technology? Now, to handle some of these problems, what researchers have been doing is looking at different kind of devices. And one side, we have the single gate devices and variants of single gate devices like the bulk CMOS, fully depleted SOI, or in fact even today, partially depleted SOI. These are actually certainly technologies that have worked really well, and people are possibly going all the way down to 22 nanometers even with these kind of technologies. But from the scaling point of view, having a better aspect ratio of the device, which is basically a lateral dimension to the vertical dimension of the device, it turns out that the device with gate all around, or gate having on the two sides of the channel, or tri-gates, as an example, are turning out to be quite important. And there's been a bunch of work, research work that has been done in the area of, FinFETs, tri-gates, and so on. However, I mean, again, the probability of that happening down to, 15 nanometers or 20 nanometers is there. But of course, what happens beyond that domain, there has been a lot of research work which is going on in coming up with, nano devices, non-silicon based nano devices. The idea is that, hey, can I come up with a drop-in replacement for silicon? Now, to that effect, people have looked at, carbon nanotube technologies, graphene. There's a good amount of work which is going on in, 3.5 devices, and spintronics as one of the options. But interestingly, again, there doesn't seem to be really a particular solution which is available that can be a drop-in replacement at this time for silicon technologies. So when it comes to semiconductor industries, they certainly have to look at what are the different possibilities in the future. How do I add value to my designs? Now, to that effect, I mean, if you look at that, was basically from the device point of view, the technology point of view. But turns out, from the functional point of view, there is actually a system-level trend that one can see. That, of course, digital, analog, RF, optical sensors, and so on, being put into one particular system of the size of a wristwatch. And this is actually a slide that I borrowed from, the PRC at Georgia Tech, really showing that, that kind of functional convergence is something that certainly industries and people are interested in, putting computing, digital audio, digital imaging, video, and so on into one particular device. So in order for these kind of things to happen, research has started again in different domains. And if you really look at what we call the more than more integration, is that if I look at technology generation over time, certainly people are still scaling CMOS devices, and there's a push towards actually, I mean, that turns out to be the more than more, the more domain, which is shown in red, that we are scaling our technologies, and variants of silicon are being certainly scaled over different technology generations. And there's also certainly been a large amount of work which is going on in beyond CMOS, what's going to happen in the beyond CMOS domain, and the areas that in the beyond CMOS domain, the devices that include are certainly spintronics, other kinds of quantum cellular automatas, nanotubes, nanowires, and so on. And there's active research which is going on in that domain. But interestingly enough, if you look at this one which is shown in green, is the one which is the more than more domain, meaning thereby that yes, it's possible to actually have devices which are certainly probably larger than the devices of today, like the thin film technology or MEMS, or for that matter, other kinds of biochips. Maybe one can think of having, chemical sensors or biosensors on chip. And turns out that, if I can add some of those electronics along with CMOS, then I can get a large improvement in my functionality, certainly, and of course, lower cost. So some of those technologies that I'm talking about, which are sort of in the more than more domain, are the domains where it's going to be low cost. Sometimes you're not going to be able to implement them with standard silicon CMOS process. So that turns out to be important as devices which can be sort of integrated along with standard CMOS technology to get more functionality. Otherwise, which you wouldn't be able to do it with just silicon. So that's one domain that is turning out to be quite interesting. And to that effect, I'll talk about some of those, devices in a mixed system or a heterogeneous system. So just to sort of differentiate, if you look at today's IC, there's certainly a trend today with 3D stacking of traditional silicon dies. So people have been actually started, and IBM has done that. 3D stacking of traditional silicon dies to get better performance, to improve the interconnect cost, and to overall have lower power at the same time, better performance. Integration of passives into your devices certainly is important, and in the mixed signal domain that turns out to be quite important, and people have been doing that, having inductors and so on integrated into today's ICs. And of course, the trend has certainly been integrating RF mixed signals and so on. But that's not the domain that I'm really going to be talking about. And that's hybrid certainly, but that's not the domain that I'm going to be talking about. I'm really going to be more focusing on some of the more than more devices, the devices that can sort of give you auxiliary or ancillary functions to silicon CMOS and give you low cost and lower power consumption, better robustness. Actually, we actually had a presentation, and initially I called it the chip of 2020 because that's really sounded good. But this is actually a chip-level view of the future chips of that one can potentially think of. So this is a sort of like a microelectronic city, and the interesting thing is this, comparison with that city. So one can potentially think of having, for example, a central processing unit. That's like building 1. Building 2 is another central processing unit, and it can be stacked with different, processors and so on. And on top of that, actually you can have at the same time highway, which is a channel connecting, for example, memory units, which are shown over there, which is, high density garage or storage elements. One can again think of having a city hall. What does a city hall do? It basically is going to do some sort of power management. In this particular case, there is a power plant right here, which that turns out to be quite important. And what kind of power plant we are talking about here? We need to do some sort of energy scavenging. That is becoming a real issue. The question, of course, is you might have built-in solar cells in there. You might also, at the same time, scavenge energy from vibration, depending on the kind of application that you're looking at. You might actually scavenge energy, from, all kinds of other sources, RF and so on. Then on the other side of it, certainly one can think of having a nano biochemical lab, and this is kind of interesting, is at Purdue, our group and, the chemistry department, we are actually working together to see the possibility of having sort of a on-chip mass spectrometer. Now, what a mass spectrometer can potentially do is that if you can have it on chip, and that's certainly not very easy to do, but if you have it, you can almost have it in your cell phone, so to say. So, and it can sense biological element or other chemical elements using this mass spectrometer. So, this sort of an integrated system where you can almost sort of, put everything into that system. But some of these devices, as you can see, these are not going to be small, and these are certainly not, more devices or beyond CMOS devices, though, beyond CMOS devices can certainly be integrated into the system too. The other interesting thing to look at is that, you have a hospital which is basically doing nothing other than, self-correction, self-healing, and so on. So sensing, self-correction, self-healing. The other interesting thing, of course, is that one can think of having a, thin film OLED technology, having, DLP. So now you can actually project from your cell phone to it, so to say. And by the way, that technology is available today. So the objective then is improve traditional metrics such as performance, storage, and so on. And I'll talk about some of these in the later part of the talk. And to achieve that, it turns out that, in the earlier slide, I showed basically that, there's a highway connecting, copper channel connecting, for example, different systems right here, or different subsystems right here, but there's a possibility of having wireless communication, right? And in fact, you can project, or at least you can send data over wireless links between different subsystems in this particular case. So you can there's a need for talking about very high density storage elements, and to that effect, I'll talk about some of the possible high density storage and different work that's been going on in that domain. And to facilitate system level convergence, DLP technology, chemical and biological sensing, which I'm not going to be talking much about in this lecture, but certainly auxiliary functions, and I'll spend quite a bit of time on that, having online test and verification. So what do we really mean by online test and verification? I'll go into more details of it later on, but turns out if you look at a microprocessor of today, it's the test cost or the verification cost, if you talk to the engineers, it turns out it's actually as expensive as the design cost, right? If not more in some cases. So the question, of course, is it possible that I can use some of these more technology to do online test, online verification of the system? So to that effect, I'll talk about some of the implications of that in some of the later slides. Low cost, that turns out to be very, very important. People have started looking at printable electronics, and if I can actually add that electronics into my system, again, I can get a lot of these heterogeneous integration and functional convergence. So in order to actually have this, one can potentially think of this kind of heterogeneous integration, and so that's sort of an alternative paradigm that can enhance the product value. The few of the things that I'm going to be talking about today are CMOS, well, not so much in the optical wireless part, I'll briefly talk about it, but, CMOS and 3D integration, CMOS plus, for example, thin film technology for low cost, test applications, CMOS plus MEMS technology for, low power. So potentially what one can think of is a system, and a 3D system in this particular case, a heterogeneous 3D system. So you have the standard silicon CMOS circuits along with RF and analog. On the second layer, basically in blue shows optimized, in this particular case, optimized low temperature polysilicon, thin film transistors. These are very low cost transistors. And the idea is that, hey, if I can somehow come up with a methodology to implement test circuitries in these low cost technology to verify the underlying CMOS circuits, then I actually have a win-win situation that becomes a really low cost alternative to robust design. And then, of course, at the higher level, what I'm really showing is that we have energy harvesting, and this is actually 3D kind of integration that I'm talking about. But certainly it can be in 2D too, and because some of the communications that I'm going to be talking about are sort of the wireless communication. And in fact, interestingly enough, wireless turns out to be cheaper, as we'll show in some of the later slides. Yeah, it's 3D is not just a possibility. I mean, it has happened. IBM has shown 3D stacking of silicon dies, and there was a DARPA program way back in I don't know when, right after I joined Purdue back in the mid '90s, I think, where we were actually looking at with Professor Jerry Newdeck 3D integration of the double-gate CMOS circuits. But it's certainly a reality. Stacking of dies is certainly a reality. So to get started, let's talk about, as an example. So it's sometimes difficult to understand, but let's talk with an example of these thin film transistors and how that thin film technology can really be a low-cost alternative to robust design of CMOS circuits, or robust CMOS circuits. As I mentioned earlier, the complex, if you look at complex CMOS circuits, and this is actually some curves that I borrowed from SRC, it really shows that test data volume is increasing with complex CMOS circuits. So if you look at different technology generations, which is shown in terms of the years, versus the number of patterns required to do testing, that's increasing. And that's increasing at an alarming rate, right? Just to make sure that you have very high confidence that your circuit works, you have to apply a good number of test vectors, right? From a layman's point of view, if I had 100 inputs to a circuit, and if I need to verify, at least from the functional point of view, that it really works, and it's a combinational circuit, then I need about 2 to the 100 vectors, right? Sort of a nice way of doing it. I mean, if you think of applying 2 to the 100 vectors to a circuit, and one vector takes 1 microsecond, that's going to take you years to test one circuit, right? So that's not a way that you can really test your circuit. So people have come up with various interesting ways of testing and verifying CMOS circuits. And that, by the way, I just talked about is actually a combination logic circuit. So if things are sequential, things become even worse. And the other interesting thing to note is the fact that verification is becoming really, really problematic. And if you look at, and these are actually some of the design bugs reported by industries. So interestingly enough, the first few months of the design, after it's been done, turns out you can get a good number of bugs. So on-chip verification, on-chip testing of the CMOS circuits are becoming important. And in fact, if you really talk in terms of reliability, and if your, for example, threshold voltage is going to vary over time because of stress conditions and so on, so there's a need to figure out, hey, I mean, is it still working, or am I getting garbage outputs? So that's the basic domain that I'm looking at in this particular case. And so the application, but as I mentioned earlier, that I'm going to be looking at CMOS plus flexible electronics. So if I look at the application space for flexible electronics today, which is sort of the macro electronic domain, it turns out that people certainly have been doing different systems on panels. These are all different possibilities. Smart surfaces. People think in terms of having a skin sort of structure, artificial skin. You can think of putting your devices or sensors on plastic substrate, and that can be sort of like sensing something cracks in certain areas of. It could be in the body of an airplane and so on. And I'll give you some examples of some of the work that is going on at Purdue to that effect. Biomedical sensors, and as I said, system on a panel and so on. So, but if you really look at most of these transistors, and today they are certainly used, the TFTs are used in any one of these displays. They probably work with 10 to 15 volts, and they're not very good transistors. They're actually pretty bad transistors. So now, if I really think of going to use it along with standard CMOS circuits, then I have to face several different kinds of problems. The problems that turn out to be important are that I have to have CMOS compatible operations. I can't possibly use a 15 volt VDD for those devices. And second, the devices have to be really small. Certainly I'm never going to have the performance that I would have with my bulk or silicon CMOS technology. But here I'd like to get reasonable performance. And what is reasonable, I'll talk about later on. Reasonable performance so that I'm able to do some online verification and online testing. So remember, I'm not doing, full-fledged testing of these circuits. I'm not really doing some, at-speed testing, but I need still to do, reasonable verification of these circuits. So now I have to actually optimize my devices maybe into the nano domain, so to say, to get some performance and to see what kind of possibilities I have, making sure that I'm still in that low-cost domain, right? I don't want to get away from the low-cost domain because then the entire purpose is lost. In general, if I look at thin film transistors, there are several issues that I have to look at in general. And on the right side, which is shown right here, is a transistor which shows a source and the drain of the transistor, and using polysilicon channel material. So if I'm using polysilicon channel material as opposed to crystalline silicon, one of the advantages of crystalline silicon, of course, that if I'm using polysilicon, there'll be grain boundaries, right? And what are those grain boundaries like? In general, due to these grain boundaries and having traps over there, what's going to happen is that my mobility, overall mobility, is going to decrease, right? And if I look at sort of a equivalent band structure, what I'll see is that there are potential barriers in the region where there are grain boundaries. Now, of course, I don't know where the grain boundaries are going to be. That's one issue, and we'll talk about that in just a minute. But the other question, of course, is that how many grain boundaries should I really have? You know, if I have a large number of grain boundaries, then of course, you know, in these large TFTs, then my mobility is going to decrease quite a bit, and I may not kind of have the performance that I'd like to have, and I may not still be able to operate the devices down to about 1.5 volts or so, which are CMOS compatible voltages. So what we did is actually looked at different process technologies, and it turns out that you can use laser annealing process and still be able to get a reasonable transistor down to about 200 nanometers or so. Now, if you are using 200 nanometers, and if you are using, for example, a process temperature of, let's say, maximum temperature about 400 to 500 degrees centigrade, it turns out, you know, you can get grain sizes of the order of about 200 nanometers or so. So if you get grain sizes of the order of 200 nanometers or so, then one can potentially think of having a device where there's going to be maximum 1 or 2 grain boundaries. And then what I really need to do is figure out, hey, what is going to be the degradation in the transistor and so on. But there's some very, very interesting thing to note in such a technology right here. The interesting thing to note is the fact that this is not a bulk technology. What does it really look like? It looks more like an SOI technology, very thin body SOI, right? I mean, very thin body, I shouldn't say. I mean, if I can make my body to be really thin, then of course it looks like a good transistor. Of course, there can be grain boundaries. So what we really did then is that I know that I have another constraint. The constraint being I may not be able to use, high temperature. If I'm not using high temperature, my, oxides may not be of the best quality. So I have to be worried about that too. So the issues turned out to be the free carriers are trapped by the grain boundary regions, so the GB regions. The potential barrier due to the depletion region is going to actually have a reduced effect of reduced mobility on these transistors and reduced number of free carriers. So to that effect, actually, what we did is actually we did optimize these devices under certain constraints. The constraints being the process technology constraint, right, and the temperature constraint. So for that, the design principle that we used is using an alternate scaling rule. So what do we really mean by an alternate scaling rule in this particular case? So I'm not going to be able to scale I'm not going to be able to have a good oxide. So even if I'm not scaling my oxide thickness, the question, of course, is can I get a reasonable transistor out of it? And it turns out it's possible by actually having a body thickness of that device to be reduced. So my scaling is going to be a little bit different. I'm going to use laser annealing process, and due to that, I can get very thin body devices. Devices of the order of about 20 nanometers, or in fact 20 to 25 nanometers I can get TSI. So if I can get that, now what happens is that I can make the right kind of trade-offs. So one can show that, and I can make the right kind of trade-offs with body thickness optimization versus not having the best of oxide. The second thing is that the manufacturing solutions is certainly looking at is hydrogenation to reduce the mid-gap trap densities. And so using those two solutions, what we did is we actually plotted the standard silicon devices. We actually compared a 200 nanometer silicon device. In this particular case, a silicon device is actually an SOI. I think I'm not really sure if I considered SOI in this particular case. But anyway, the crystalline silicon versus I looked at these kind of devices which are very, very similar to a thin body SOI. Of course, in a standard thin body SOI, I would like to make my body thickness even smaller and my oxide thickness to be smaller too. But it turns out, if I really were to compare crystalline silicon with some of these polysilicon technologies having, different grain boundaries, in this particular case, the red one shows a grain, having one grain boundary, and this is I think it was a 200 nanometer device. And if I look at a polysilicon with 9 grain boundaries, what you really see is that the characteristics of these devices. So that's, if you do the right kind of optimization, it turns out you can get a reasonable device. It's not going to be the best of devices. You're not going to be really trying to replace silicon with those devices. But the question, of course, is, hey, can I really do what I want to do? And in this particular case, doing online verification and test. These are some of the other ones showing the, more details of this manufacturing process. But more important thing to note in this particular case is that you can have different kinds of, absolutely, you don't have repeatability. So we'll have to talk about it, yeah. So the thing is that, the modeling techniques that we used is basically having these different grain boundaries, and we actually, I'm basically showing the channel region which was divided into several areas where we could decide to put a grain boundary or not. And so this actually work appeared in the Transaction Electron Devices published, I think last year or the year before. And again, using the design principle that I just talked about. The few things that one has to be careful about is repeatability. And so I'm going to be facing the problems. It's even more of a problem than what I had, for example, I have in my silicon technologies, right? Due to random dopant fluctuations, I have variations between transistors. Here, I have variations, and these are random variations due to the number of grain boundaries in the channel, position and location of the grain boundaries in the channel, right? Just like in the random dopant fluctuations, I have to worry about it. And at the end of it, I have to also worry about, is it a longitudinal grain boundary or a latitudinal grain boundary? Now, of course, there are process technologies where I can use possibly and to have, grain boundaries only in one direction, and that's possible. So what we did is actually we looked at the possibilities of, how much of a variation am I going to have on some of these benchmark circuits. We looked at inverter with a fan out of 1 versus, some of these ISCAS benchmark circuits, and in this particular case, this particular one had a good amount of variation. A few interesting things to note is that variation certainly depends on the statistical placement of the grain boundaries on a die. When the logic depth is small, like 1, 2, 3, 4 kind of things, they can actually affect us a lot more because these are random ones, so the cancellation effect is not going to be there. But if I increase the logic depth to, in this particular case, huge, 29 or so or 30 or so, it turns out I can get a unimodal distribution rather than sort of a bimodal distribution that I was getting earlier. So it turns out variation tolerant design is certainly a very challenging task. And some of the techniques that we've been using in silicon, I may not be able to really very well apply it here. And the techniques that I was using is more sensing and correction. And that doesn't make sense in this particular case, right? Because these are actually used for some low performance applications. So the one that really comes to my rescue is basically what you do in analog design. And in fact, these days, even in digital design, that you really do is multi-fingers, right? Rather than having one finger, you actually have multi-fingers. And if you have a normal TFT versus a two-finger TFT, one can, do an analysis of it, statistical analysis of it, and one can show that, you can have, from the variation point of view, that this one with a multi-finger is way better than having, a single finger. Right? So that's basically the one that we looked at, along with the fact that in this particular case, I might actually have to do reasonably worst case design. The other interesting thing to note is the fact that the multi-finger design turns out to be a little bit different from having a wider transistor in this case. And the reason why it's a little bit different than the wider transistors is if I have a wider transistor, I'm going to be dealing with a lot more grain boundaries. And in fact, if I use actually multi-finger structure, I'm going to get a better design because of the cancellation nature of it. So then what we really did is we actually looked at the digital, DSP mixed signal and all kinds of different circuits in this domain, and then came up with a genetic test structure, which is basically going to test the underlying CMOS circuits. So these are, some of you might be familiar with the built-in self-test. Some of you might be actually, potentially think of having on-chip oscilloscopes. Or one can potentially do, on-chip, whatever, you can actually measure the speed of certain sections of the circuit and so on. So it's almost like having an on-chip tester that one can think of, right, in that TFT. And so these are scale devices. They're certainly not down to, 50 nanometers or so, but in 200 to 250 nanometers, I can really think of having, on a glass substrate, a bunch of unit test structures. And what I'm really not talking about is what are these different test structures like. So if you're interested, I can refer you to one of our papers. So what are the different test structures like? But the interesting thing is that, yeah, that would give me something that I can test my underlying CMOS circuits. And I can offload some of my test cost from external tester into this CMOS circuitry. So a very simple-minded analysis would do. I mean, those of you are familiar with linear feedback shift registers and so on, and those people have been using it in today's design a lot. So what potentially one can do is you have the CUT, which is a circuit under test, and along with that, on the two sides, you have these LFSRs and the misers. Misers are also some sort of a compactor. And so those are there in the circuits, and one can potentially think of moving all these, LFSRs and misers sort of into your TFT domain, along with all these extra, unit test structures that I've been talking about, to test or verify these underlying CMOS circuits. And it turns out, and this is actually some of the simulation results that we actually built, model the devices, with the new scaling methodology, and then we were able to actually characterize and simulate these devices to show that, yes, it's possible to actually use, have reasonable power consumption of the order of about, in this particular case, for testing some of these multipliers that we looked at, about 20 to 40 microwatts. And the frequencies of operation turns out varied quite a bit, but from 0.8 to about 4 gigahertz. And why did I really get so much high performance out of these devices? Very thin body devices, right? And if I'm able to get it down to about 200 nanometers using the kind of process technology that I was talking about, the temperature, it wasn't really having too many grain boundaries. And the other interesting thing to note is that if I do not have any grain boundary, and that's a pretty fast device. Okay? So there's a good amount of variation too. Another thing that I mentioned that I'm not going to go into the details of it, but what we have a project in our research group is that we are actually building single chip radios, but self-powered radios, very low cost radios. Now in this particular case, what you really have to do is you have to optimize your digital devices, but certainly your analog devices have to be optimized too under the same constraint. And at the same time, you probably need some RF devices. The kind of applications that we'll be looking at, I'm working with some of my colleagues in the networking domain, is sensor networks, right? You can really think of having very small devices, all around communicating with each other. And then along with that, you need to have, actually there's a work which is going on in our group, along with Professor Alam and so on, is on polysilicon or amorphous silicon solar cells. And what we've been looking at is basically not large area kind of electronics in that case, but very small area electronics where energy scavenging is going to be there along with very thin sheet battery. And the idea is that I'm going to be actually, since these are not going to be very active devices, the idea is that I'm going to be storing some of those, recharging the batteries using these solar cells. And we actually have a paper on that in the Design Automation and Test Conference in Europe this year. So again, the similar kind of device optimization modeling, and the modeling techniques are a little bit different, but here we're really talking about is analog circuits. And just wanted to mention that we actually looked at a very simple-minded, op-amp. This is not the standard 741 op-amp, but a very simple-minded op-amp is what we looked at. And the idea is basically, how can I get in, from analog circuit point of view, improve transconductance. We need to ideally need to scale our oxide thickness, but again, the quality of the oxide may not be the best. But how can I get higher GM and R out for higher gate controllability and so on is what we've been actually looking at. And to that effect, actually, we have a design flow that we have from Taurus ADS to SPICE, and the work is still going on, as I mentioned, regarding the radio aspects of it, but we are not still done yet. But as I said, some of the op-amp simulation, it's not a very good performance op-amp, and we still have a lot more work to do. But the idea is that, hey, can I use the same technology for all these sort of things? But here, the device circuit and to a certain extent architecture co-optimization turns out to be quite important. So the other thing that we looked at is CMOS plus MEMS. So I thought I'll just briefly go over that. And here the idea is ultra low power. And back in the late 90s, we are the ones actually who proposed sleep transistors, or actually stacking effect. Looking at a stacking effect. And if you look at one transistor, NMOS, if you take an example of one NMOS transistor which is turned off with the drain connected to VDD and the gate and the source connected to ground, turns out you're going to get some leakage, right? Leakage I, let's say. But if you have two transistors in stack, series connected, and both are equal to 0, the gates are equal to 0, it turns out that leakage is going to be way better. And the reason why your leakage is way better is because the top transistor is going to have a VGS. Because of a little bit of leakage current flow, the VGS is going to be negative, right? So a negative VGS can give you a huge improvement in a leakage current of the order of about maybe 8 to 10x. So certainly you can get a large improvement, but the question, of course, is, hey, is it possible? And in the one can very well use it in the standby mode, and people have shown that I can use it in active mode of operation by actually doing some pre-computations and so on. But the interesting thing to note is that the number of transistors in stack versus the leakage improvement from 10x, it goes down to, you can get a large improvement, but you can be very greedy and say, hey, why do 2 transistors stack here? Why not 3? Why not 4? There's a diminishing return beyond a certain point. So one can very easily show it mathematically can be shown that the maximum improvement is really, since it's an exponential region, really from the first transistor, that is huge improvement in VGX. The other ones are not going to give you that much of an improvement. But anyway, the interesting thing is that if I can somehow get rid of that completely and use MEMS switches. So rather than using transistors, I'm going to use mechanical switches. And turns out that you can get a large improvement in this particular case. The only problem is that if you use MEMS switches, you're going to lose the value. When it comes to some of the stacking or the slip transistors, I do not lose value. I do not lose value even in memories. If I do it properly, I do not lose value in the memories. But in this particular case, if I actually use mechanical switches, then I have zero leakage. So we call it zero leakage CMOS. These were integrated along with the transistors, but the important thing to note is the fact that I'm not going to have any, I cannot do that in memory part, right? I'm going to lose value completely in the memories. And the second thing that turns out to be quite important is that you have to really figure out what kind of MEMS switches that you want to use. And those of you are familiar with some of the MEMS technologies today and what others are looking at, one of the major factors is that the reliability of these switches are low. And the reason why the reliability of some of these switches are low, these are mechanical switches, sometimes people do get stuck. And if you'd like to have very high frequency of operations, the number of switching that you can potentially do is not too many. So one, since Maryam suggested that we look at, in this lecture, mostly from the application point of view, another application that one can think of is a cell phone kind of application where the activity level, meaning thereby that I'm not going to be turning on my system all the time. It's really mostly in the standby mode of operation. And if I do that, and then my reliability turns out to be reasonable. And this is actually a joint work that we did with Dimitri Peroulis, and I acknowledge everybody at the end of it, is that we looked at different kinds of switches. And we looked at different switch structures, the individual switches versus the mesh of switches and so on. So we looked at electrostatic, thermal, magnetostatic, and the piezo kind of switches. And it turns out that for the kind of applications and the things that we're looking at, the thermal switches were actually quite good. And we looked at 3D integration of these switches. But as I mentioned earlier, these are actually some of the SEMs of this bimetallic cantilever MEMS switch that was developed. Issues certainly are the reliability of the switches, integration with CMOS, and low voltage actuation. That CMOS compatible operation, that turns out to be important. Now, what we did then is that once we characterized these switches, we wanted to see how much of an improvement can you really get from a systems perspective. From this particular application, we looked at a cell phone, and this is actually a cell phone basically showing different how much is the SRAM energy and how much is basically the logic energy and so on. But most important thing to note is the fact that if I were to use MEMS switches and use it for leakage control and looked at different kinds of batteries, lithium ion and NIMH kind of batteries, what it turns out, bottom line is that the proposed methodology sort of can give you potentially And of course, it really depends on how much of a memory usage you have versus you don't. And the alpha factor, which is shown there, shows how much of a memory usage that you have for your system. So it turns out that if you have less of an activity in your memory, you can turn off your memory for a longer period of time. And it turns out that you can get almost a 2x improvement in energy of the system, meaning thereby you have 2x extra battery life. And for a central kind of application, that turns out to be interesting. And the other thing to note is that reliability, at least, what we calculated, wasn't really much of a problem. Because of the fact that we are not switching, very fast. It's basically switching once in a while. Finally, I just thought this is important. Any kind of, high performance device that you really think of has to have a lot of memory. And, by friends in the architecture community, they tell me, and in fact today if you really look at, high performance processor, and you certainly have a lot more transistors that are available every technology generation, and where do these transistors really go? Turns out mostly the memories, right? And the memory size of a high performance processor today, if you compare to the rest of the circuit, I mean, from the die area point of view, they take about 70 to 80%, right? So you put more in the memories, on-chip memories, so that as long as you don't have to go off-chip, you get a better performance. And so that's a reason why we need to really think in terms of very high density memories. And so in this particular case, what we really did is we looked at a spin torque and spin torque MRAMs, and there's a reason why people are looking at spin torque MRAMs as opposed to the standard MRAMs. It turns out that the spin torque, I mean, any device that you look at has to be more scalable. And turns out the spin torques are more scalable than the standard MRAMs which are available today. And by the way, this is actually one example of a sort of a beyond CMOS kind of device from the spin domain. Just very quickly going over issues with, and I'm going to be talking about probably some of the spin stuff on Tuesday's lecture. But one of the things that we've been actually looking at is, and so are a whole bunch of other folks, is that magnetic tunnel junction. And that would actually have a ferromagnet on one side and two ferromagnets, and in between you actually have a very thin oxide, or it could be actually a metal, depending on whether you call it a spin valve or a magnetic tunnel junction, like using the oxide. If one of the ferromagnets is going to be a hard magnet, meaning thereby that it's going to have a up or down spin, and the other one is going to be a soft one which can be changed. So the interesting thing to note is the fact that if I look at such a structure which is shown on top, two ferromagnets on the two sides, the right side is basically the normal metal for connection. It basically shows two spins in two directions, the same direction, up direction, and in between sandwiched the channel, and the channel being actually some sort of an oxide. And the thing that happens is it's basically a tunnel junction that I'm looking at. And if you look at the ferromagnets, they have some interesting characteristics. If it's predominantly upspin, then the structure that is shown on the EK diagram that is shown on the left is what you're going to be seeing. Versus if you have one which is minority spin being the upspin, you're going to look at on the right side. So interesting thing that happens is if you inject, for example, an upspin, then it's going to go in, but since the right side is dominated by the downspin, it'll get reflected. One can show. But what happens is that you're going to get a resistance in the anti-parallel domain, which is going to be different from the fact that if those were both upspin. So if they're both upspin, then what happens is it comes in, and again the right ferromagnet is also upspin, and that it's going to go through. And due to that, the difference in resistance from the two different configurations, the anti-parallel and the parallel configurations are going to be different. So it turns out that this can be a sort of one has to do a self-consistent analysis of it to figure out, how fast I can switch. The second thing is that from the static point of view, I also figure out would I be able to switch, and so on. So one has to solve the spin-dependent transport, which is the NEGF, along with basically magnetization dynamics, which are the energy equations. So if I self-consistently show basically, and we've developed it, and it shows basically that I can, match with some of the experiments and so on. But the interesting thing to note is that what I'm really going to be doing is that if I have the right kind of MTJ structure, it turns out I can actually do I can have two different resistance depending on whether it's anti-parallel or parallel. I'm going to skip this. It turns out there are some tri-layer junctions are actually good, but you can possibly get a better difference in the resistance if I were to have pentalayers. Of course, the fabrication of pentalayers are going to be a little more difficult than the tri-layers. And we've been looking at some of those, but actually the pentalayers give you better memories. So the interesting thing to note then is the fact that if I were to actually use a structure which looks somewhat like this on the left, which is an equivalent circuit, would be I have this magnetic tunnel junction, and this is the hard magnet, right? And this is a soft one. I can change it depending on if it's by proper current. Writing proper current either from the top or from the down. I have to so writing turns out to be actually a little bit different than the right. I have to figure out whether to have current from the bottom or the top. And if I do have a structure like this, by sensing whether it's a high resistance or a low resistance, then I can actually have a memory, right? So this looks like a memory structure. I still need actually one transistor, and so my area of this magnetic tunnel junction turns out to be of about 10 nanometers by 10 nanometers by 10 nanometers or so. And so this, if you're looking at 130 nanometer technology, or if you're looking at a 65 nanometer technology, so your area is still dominated by the area of this guy. And it turns out that this structure is more scalable than the kind of the MTJ structure is quite scalable. And if you scale it down, the right current requirement is going to go down. So I'm not talking much about the right current requirements at this time. It's still actually pretty high, but way better than MRAMs. So in MRAMs, what you really do is that you don't use spin torque current to change the magnetization of one of the free layers. In MRAMs, what you do is you have an external field, and this external field is applied to change basically the magnetization. And unfortunately, what happens is that if you have an external field, one can show that concentrating that magnetic field is very difficult. So you need some coils, and maybe you have to introduce some high permeability material inside and so on. So all those different things that you have to do, and there that becomes very difficult. So from the scalability point of view, if you have a nanomagnet, one can show that spin torque is better. In fact, very recently, and this is a reality today, is the fact that yes, Sony actually did. I think it is Sony who fabricated this kind of devices and a memory structure actually. So the good thing about it is that compared to SRAMs, non-volatility and the kind of things which are important from the memory point of view, cell size, read time, write time. The write turns out to be actually not as good, right? The write current turns out to be actually high. But other than that, power consumption, the leakage power consumption is 0, and all those sort of things are extremely good for these kind of devices. Variability is still a problem, which what one can show is that this is actually the same slide, but the variability turns out to be a problem. If you look at the area of that MTJ structure, and if there's a variation in the oxide thickness, then turns out there's going to be a good amount of variation in that resistance. And hence, what happens is that you can actually see some failures. So variation is a major problem in these kind of memories. So people have done different kinds of things. What we looked at is rather than, remember that in the last lecture I was talking about that read and the write has to be separate, or if, ideally if you can separate it, that turns out to be good. And that's exactly what is done in the second one, that I have everything I can separate using 2 separate transistors. So now, if I use 2 separate transistors, I pay in terms of area, right? And that's a problem. The second thing, of course, is that any architectural solution that is, hey, I'm going to make my, read to be good, write to be bad, or give write a little more time. And then it turns out you can do various kinds of things, like the last time I talked about. So these are some of the results of analysis, which is basically considering that I have a microprocessor and I'm using this kind of memory structures in my L1 caches, L2 caches, and so on. So there's some interesting results that show that I can get a large reduction in standby power in MRAMs, that reduction turns out to be quite a lot, 89% reduction compared to SRAMs and about 70% compared to DRAMs. Turns out the major problem in all these analysis that was done is that the write power turns out to be actually worse. So now the question, of course, is if you're in the architecture area, working in the architecture area, the question is, can you optimize your writes? And there are different ways of optimizing the writes. I'm not the right person, to talk about those things, but write turns out to be less important than read in most of these architectures. So you can have different write methodologies, write back schemes and so on, which is going to give you improvement. And again, showing that you can have a huge memory in 3D, and it can, just because you're able to replace DRAMs in some of these cases, you can get a large improvement in performance in most of the designs. So just basically showing from the application point of view, these do make sense. Finally, and this is actually Byung-gu is one of my colleagues, is actually working on this, Professor Jung. And what we did is actually looking at this kind of 3D hybrid structures. But the question, of course, is that what kind of communication methodologies that I need to use for any one of these kind of hybrid techniques. There are limits to copper wire links, limited bandwidth due to intersymbol interference and so on. Severe attenuation is possible and distortion at very high frequencies. And to that effect, so what he did is actually looking at the possibilities of copper plus optical communication, and in and these other cases, what he also looked at is copper plus wireless communication. So this is actually a chip that was fabricated, showing the bond wires were used as antennas for communication between two chips, and he got results of, and it is fully compatible with CMOS technology. He got 6 gigabits per second and 17 picojoules per bit has been demonstrated, and this, by the way, was actually judged to be the best SRC design contest work. Just one another application, talking about, yes, it's published, yeah. I think it's going to be nice at CC this year. Application is, this interesting work which is going on at Purdue, and this is actually a joint work between several faculty, is that a stamp-sized self-powered wireless sensing and signal processing unit is being developed. The idea is that to monitor real-time, to condition monitoring of the structural defects in aircraft components. So the interesting thing again is to note is that on flexible substrates to have these sensors to detect cracks, and then there's on top of that there's an energy harvesting layer. And remember, in an aircraft body there's going to be a good amount of vibration. So vibration is actually going to be used for these, and then of course RF communication between different layers. The second layer is that there's a flexible thin film battery, and of course for communications we have also printed antenna. So this is actually a very compact structure, and which is being actually developed at Purdue. Professor Jung, Professor Perulis, they're all involved in this. So this is actually kind of very, very, from the application point of view, it's a very interesting structure. Come to some sort of a conclusion, and then people can go on. I mean, you can go on talking about these different things. But we all know that challenges to scaling are certainly threatening the ability to provide value from successive technology generations. And that's becoming one of the issues, one of the major problems. Turns out that, and we feel that heterogeneous integration can lead to low cost, highly robust, complex systems. The interesting thing is that you need to still optimize most of the devices that are sort of available in another domain because of CMOS compatible operations, and that's where some of these, technology aware, optimizations, technology aware circuit optimizations, technology aware, circuit aware device optimizations become really important. To have low voltage operations, and of course, to make it happen, one certainly need CAD tools and different design methodologies. So this was actually, I'd like to acknowledge, Professor Byung-gu Jung. These are all professors at Purdue University, Dinesh Perulis and Anand Raghunathan. So this is actually a large project. So different people are involved in this domain, and finally, really most of the work that I presented are really all my students. Yeah, they are actually thinking of placing it in the engines. So this is actually, this is going to be considering reasonably high temperature. There are several issues that one has to look at. I mean, basically looking at these different thermal gradients and how they behave and so on. But this is sort of the idea was just to show a prototype that, things can potentially be interesting. And the communicating, I mean, you have different sensors, different sort of, you can apply it as a skin, and they'll be communicating through some, wireless communications. Yeah, I mean, that's what they used in this particular case. They didn't want to put in extra things in there, but they also, remember the other slide that I was showing is that you can actually do inductive coupling also in some of these communications. So you do put inductors and you do inductive coupling. So all these are actually, and the last one was actually having an antenna at the top. So it depends on the situations. I mean, what the bond wires were used, and they used actually for communication between two chips, which were actually the DRAMs and the processor. Yeah. The thing is that these are all possibilities, but the idea was that can we really do it? So the proof of concept was more important, and then whether it's makes sense finally from the application point of view, from all this point of view, it depends on the kind of design environment you have and so on. So, but you're right. I mean, there are lots of still different. As I mentioned, design methodologies required and. Certainly modeling and CAD tools are also not there. So what was done basically using, the things which were available and modelings that we did. Some of those were separate too. I mean, right now it's putting things together. Yeah. I mean, it's not that we have a tool which just flows everything smoothly. And also I just wanted to mention that's not the aim either. We're not selling the tool. To that effect, I always say that we are not in the business of making money. I wish we were, but no. Yeah, it is available actually. I mean, so basic point to note is the fact that it's a reality, so to say. It's high density as possible. There are lots of issues to be still solved, but it's still a reality. Yeah, again, that's why I took advantage of Maryam's class, saying that it's a mixed signal class, and she kept telling me that I should talk about applications and analog. And since I'm not really the analog person, I thought, okay, mixed one I can do. Different mixed technologies. So they say, yeah, but RF CMOS, that's the standard one that people have been looking at. In fact, integrating passives. So from that angle, yes, things have happened. Integrating passives, absolutely. Could be, but then again, if you really talk in terms of, it depends on how you stack it or how you place in the 3D, each of the layers might need some RF part. Right? The last one that was shown there was for a very particular application where they're putting each layers, and it could have RFs in the different ones. But here we're talking about, yes, you might need actually RF in the TFT layer. You might need RF in the CMOS layer. Yeah, that's why you need to optimize your devices also for these RF applications. So when we talk about this, radio and very low cost radio area, those kind of optimizations have to be looked at. The very fact we're doing it is because. Why are we using it for these kind of applications? Because it doesn't have the performance, right? It's not going to have the right kind of performance. So, can I use some of these quote-unquote bad devices, make it a little bit better, and use it? Otherwise, I'll be using everything on the glass substrate and get the highest performance.
Okay. Thanks a lot, Professor Rai. And